At 12 kilometers underground, the rock stopped behaving like rock. It started flowing. That is not a metaphor. The stone, ancient 3-billion-year-old granite, began to creep slowly back into the borehole, like something alive trying to close a wound. Every time the drill bit was pulled out for replacement, the hole would begin to seal itself. The earth, it seemed, did not want to be opened. This is the story of the deepest hole ever drilled by human hands. A hole so narrow you could not fit your arm inside it, but so deep that a coin dropped down the shaft would take 50 seconds to hit the bottom. It sits in the frozen wilderness of northern Russia, above the Arctic Circle, welded shut beneath a rusting metal cap bolted into a crumbling concrete floor. And what the scientists found on the way down shattered nearly everything geologists thought they knew about the planet beneath their feet. They found fossils, 24 distinct species of microscopic marine organisms, 2 billion years old, preserved 6 kilometers underground with no explanation for how they got there. And at the very bottom, they found something that forced them to stop, a wall, a physical limit that no machine on Earth could break through. And then they sealed it in concrete and walked away. Before we get there, you need to understand what was at stake and why two superpowers spent decades and billions of dollars trying to dig a hole. We know the crust, mantle, and the core, but all of this from indirect evidence, seismic waves, laboratory simulations. But we have never actually retrieved a sample from the mantle. Everything we believe about the deep interior of our planet is, in the strictest scientific sense, educated inference. That is the gap the Kola Superdeep borehole was built to close. The race to the Earth's interior began the same way the space race did, with competition, with Cold War politics, and with scientists who genuinely believed they were on the verge of something extraordinary. In 1957, an informal group of American scientists called the American Miscellaneous Society proposed drilling through the ocean floor to reach the mantle. The crust is thinner under the oceans. The logic was sound. They called it Project Mohole, named after the Mohorovičić discontinuity, the boundary between crust and mantle. They drilled off the coast of Guadalupe Island, Mexico, in nearly 4 kilometers of water, and they succeeded in penetrating the seafloor, reaching 183 meters below the seabed. It was a genuine technological achievement, but it was also nowhere near the mantle. Congress pulled the funding in 1966 after costs spiraled and political infighting consumed the program. Project Mohole was over. The Soviets had been watching, and they were not going to stop. In May 1970, on the Kola Peninsula in the far northwest of the Soviet Union, 250 kilometers above the Arctic Circle, near the borders of Norway and Finland, a drill bit pierced the surface of the Precambrian rock and began its descent. They were going down. The Kola Superdeep borehole was not built like an ordinary drilling project. The hole was just 23 centimeters wide, about 9 inches. You could not put your head in it, let alone descend it yourself. But width was never the point. Depth was everything. To reach that depth, the Soviets had to invent an entirely new way to drill. This is worth understanding, because it was one of the most significant engineering innovations of the 20th century, and almost nobody outside the drilling industry has ever heard of it. Every deep drilling operation before Kola worked the same basic way. You attach a drill bit to the bottom of a long metal pipe. You rotate the pipe from the surface, spinning the entire assembly, and the bit at the bottom grinds through the rock. As the hole deepens, you add more pipe sections at the top. Simple in principle. But there is a physical limit to how long a rotating drill string can be before it becomes unmanageable. The weight alone becomes the problem. A drill string long enough to reach 15 kilometers. Kola's original target would weigh over 1 million pounds. The torque required to spin it from the surface would be enormous. The stress on the pipe joints would be catastrophic. The whole thing would twist apart long before it reached its target depth. The Soviets solved this with an invention that re-engineered the fundamental logic of drilling. Instead of rotating the pipe from the surface and using that rotation to turn the bit, they designed a drill bit that rotated on its own, powered not by a spinning shaft, but by the drilling mud itself. Pressurized mud, a specially formulated lubricant, was pumped down through the inside of the stationary drill pipe and forced through a turbine mechanism built into the drill bit assembly at the bottom. The mud's pressure caused the bit to spin. The pipe above it didn't rotate at all. It just sat there, stationary, sliding slowly downward as the spinning bit below it chewed through the rock. This meant that the weight of the drill string, 200 tons by the time the hole was at its deepest, was not working against the drilling operation. It was working with it, pressing the bit down into the rock under its own gravity. The engineers controlled the rate of penetration by managing the mud pressure and the weight on the bit, not by managing the rotation of 12 kilometers of pipe from the surface. It was elegant, and it worked. But nothing about the pace was fast. The drill averaged roughly 60 meters per month. At that rate, reaching 15 kilometers would take over 20 years of continuous operation. And the drill bits themselves were a constant problem. Each bit lasted only 7 to 10 meters of drilling before wearing out, ground down by the abrasive Precambrian granite to the point of uselessness. When a bit wore out, the entire drill string had to come out of the hole. All of it. Every section of pipe, hauled up from whatever depth the drill had reached, laid out section by section on the surface, until the spent bit at the very bottom could be accessed, replaced, and the whole assembly lowered back down again. At 12 kilometers of depth, this process took days, and it happened constantly, every 7 to 10 meters of progress. The 200-ton drill string made its slow journey back to the surface and down again. For the final 5 kilometers of drilling, the total length of pipe consumed by this replacement process amounted to 50 kilometers. 50 kilometers of metal pipe worn through and discarded just to advance the drill 5 kilometers deeper. The industrial scale of the operation was staggering. Inside a purpose-built enclosure, roughly the height of a 20-story building, the drilling rig dominated the landscape of the Kola Peninsula like nothing else for hundreds of kilometers in any direction. About 3,000 people worked at the site at its peak. Engineers, geologists, drillers, support staff housed in a purpose-built settlement nearby. The grumbling of the machinery was audible around the clock, a constant low vibration that became the rhythm of life at the site. Workers described it as the sound of the earth being interrogated. When the machinery went silent, it meant something had broken. Silence was never welcome. In winter, the polar night swallowed the sun for months at a time. The drilling rig was lit with floodlights against the darkness. A tower of artificial light rising out of the frozen tundra, visible from miles away. The aurora borealis occasionally added its light to the array, green and violet curtains moving above the floodlights, while below, 12 kilometers down, the drill bit continued its slow, grinding descent through 3-billion-year-old granite. By 1979, the borehole had broken the world depth record. By 1983, it passed 12 kilometers. Drilling stopped for nearly a year, not because of a breakdown, but because of celebration. Scientists and dignitaries visited from across the Soviet Union to mark the milestone. The project had already become a point of national pride, commemorated on postage stamps, written about in official publications. Then they went back to work, and then something went wrong. In September 1984, after the drill had reached just over 12 kilometers, a 5-kilometer section of the drill string twisted off inside the hole. The torsional stress had finally exceeded the strength of the pipe. The broken section was irretrievable, too deep, too compressed, impossible to extract. They had to abandon that branch entirely and start a new sidetrack borehole from 9 kilometers down, drilling outward from the original shaft at an angle and then back down, beginning the long climb again from a depth they had already passed years earlier. Setbacks like this were not rare. They were the rhythm of the project. Twist, fracture, restart. Down, up, down again. The project was not a single clean descent into the Earth. It was a branching, iterative, repeatedly frustrated negotiation with a planet that resisted every advance. But none of the technical problems would prepare them for what was waiting at the bottom. To understand what they found, you have to understand what they expected. Before Kola began drilling, geologists had a well-established model of what the continental crust looked like in cross-section. This model was not guesswork. It was built on decades of careful, sophisticated scientific work, specifically on the analysis of seismic waves. When an earthquake occurs, it sends waves of energy radiating outward through the Earth in all directions. Those waves travel at different speeds through different types of rock. Denser, harder rock transmits them faster. Less dense rock transmits them more slowly. By measuring the timing of those waves as they arrive at seismometers around the world, geologists can build a picture of what the rock looks like at various depths, even rock they have never seen, never touched, and have no direct access to. Using this method, scientists had identified a consistent pattern in the seismic data beneath continental landmasses. At depths of roughly 7 kilometers, there was a clear change in the speed at which seismic waves traveled. They sped up. The standard interpretation of this observation, the interpretation that had been in geology textbooks for decades, that was considered settled science by virtually every geologist working in the mid-20th century, was that this speed-up indicated a change in rock type. Above 7 kilometers, granite, a lighter, less dense igneous rock. Below 7 kilometers, basalt, a denser, heavier volcanic rock. The boundary between them was called the Conrad discontinuity, named after the seismologist who first identified it. The logic was entirely reasonable. Basalt is denser than granite. Denser rock transmits seismic waves faster. The data showed faster waves below 7 kilometers. Therefore, basalt below 7 kilometers. The argument was clean, the data was consistent, and the conclusion had been accepted so thoroughly that it had stopped being debated. It was simply what the crust looked like: granite on top, basalt below, separated by a clear boundary at 7 kilometers. There was a second, related assumption built on top of this one. At the pressures present in deep rock pressures, created by the weight of kilometers of stone pressing down from above, any cracks or pores in the rock would be squeezed shut, completely. The deep crust was thought to be impermeable, essentially sealed against the movement of any fluid. Water could not percolate down to those depths from the surface. Nothing could flow through rock under that kind of pressure. The deep continental crust was understood to be cold, dry, dense, and inert. Both of these assumptions, the granite-basalt boundary and the sealed, impermeable crust, were wrong. Not slightly wrong, not wrong in their details while correct in their broad strokes. Fundamentally, structurally, completely wrong. The first error revealed itself at around 7 kilometers depth. The seismic discontinuity was real. The drill passed through a zone where the properties of the rock clearly changed, exactly where the data had predicted a change would occur. But when the core samples came up from that depth and geologists examined them, they did not find basalt. They found granite, metamorphic granite, granite that had been subjected to such extreme heat and pressure over billions of years that its crystal structure had been fundamentally reorganized, but granite nonetheless. The same rock, just transformed. What this meant was that the seismic speed-up at 7 kilometers was not caused by a change in rock composition at all. It was caused by a change in rock condition. The granite below 7 kilometers had been metamorphosed, its minerals recrystallized under pressure into a denser, more tightly packed arrangement, and this denser arrangement transmitted seismic waves faster, just as basalt would. From the surface, using seismic data alone, the two were indistinguishable. The data was correct, the interpretation was wrong. This distinction matters enormously. It means that a core principle of how geologists read seismic data, the assumption that a change in seismic wave speed indicates a change in rock type, was not reliable at depth. The same seismic signature could be produced by two completely different geological situations. Without actually drilling into the rock and pulling up samples, there was no way to know which situation was real. The basalt was not there. Not at 7 kilometers. Not at any depth in the hole. The drill passed through granite all the way down, from the surface to the deepest point it ever reached. The Conrad discontinuity, the confident textbook boundary between granite and basalt that generations of geologists had accepted as a feature of the continental crust, did not exist in the way it had been described. It was a metamorphic transition within a single rock type, misread from the surface for decades. This was not a minor correction to the existing model. This was the existing model being shown to be built on a flawed interpretive assumption. And it raised an uncomfortable question that is still being worked through today. If seismic data alone cannot reliably distinguish rock types at depth, how much else about the Earth's interior have we misread from the surface? But that was only the first surprise. When the drill reached a depth of between 3 and 6 kilometers, something impossible came up with the mud. Water, not water vapor. Not trace moisture, locked in mineral crystal structures. Actual liquid water, free water, flowing up through cracks in the granite, pooling in fractured zones, saturating the rock in a region where water had absolutely no business existing. The pressure at those depths is crushing, many times greater than anything experienced at the surface. The temperatures are extreme. The rock, by every model geologists had, should have been sealed, tight, impermeable, dry. When the Soviets reported this finding to the international scientific community, the initial response from many Western geologists was simple disbelief. Not skepticism, disbelief. The prevailing understanding of deep crustal physics was so confident on this point that the Soviet data was assumed to be an error, a contamination of the samples, a misreading of the instruments. Some artifact of the drilling process itself. Free water at 5 kilometers depth in solid granite was not something the models allowed for. Therefore, the thinking went, the Soviets must have made a mistake. The Soviets were telling the truth. Understanding why requires understanding what was happening to the rock at those depths. The pressure exerted on minerals by the weight of 5 kilometers of granite above them is extraordinary, far greater than anything that can be replicated in a laboratory at normal scale. Under that pressure, certain minerals that contain hydrogen and oxygen atoms locked within their crystal structures are essentially wrung out, the way you might wring water from a wet cloth. The hydrogen and oxygen are squeezed free from the mineral lattice and recombine into water molecules. This process, the pressure-driven release of water from the minerals of the rock itself, produced a continuous, slow generation of free water deep within the granite. That water then migrated upward through fractures in the rock fractures that, according to the old model, should not have been open at all until it reached a layer of impermeable rock above it that it could not pass through. There, it accumulated. A reservoir of highly mineralized, saline water, trapped miles underground, not descended from the surface, but generated by the rock itself under pressure. A form of water that had never been in a river, never been in a cloud, never been part of any surface cycle. Born in stone, trapped in stone, sitting in darkness at temperatures and pressures that would be lethal to any living thing. And the mud coming back up from the borehole was doing something else strange. The drillers described it as boiling, not from heat, but from gas. Hydrogen was bubbling out of the hole at levels nobody had predicted. Nitrogen, helium, carbon dioxide. Gases rising from depths where the geochemical models had not placed them, in quantities that suggested active chemical reactions were occurring in the deep rock reactions that were generating gases continuously, not as the product of ancient geological events, but as ongoing processes happening right now, in real time, in rock 3 billion years old. The implications of this were significant beyond the immediate scientific surprise. If the deep continental crust was not sealed and dry, but fractured, fluid-bearing, and chemically active, then everything built on the assumption of a sealed crust needed to be reconsidered. Models of how heat moves through the Earth's interior, models of how earthquakes initiate and propagate, models of where geothermal energy can be found and tapped, models of where mineral deposits form and how they move. All of these rested, to varying degrees, on an understanding of the deep crust that Kola had just shown to be incomplete. The deep crust was not inert. It was alive, not biologically, but chemically, hydraulically, dynamically alive in ways the surface observations had entirely missed. But the most stunning discovery was still to come. At 6.5 kilometers below the surface, more than 4 miles underground, scientists found fossils. 24 distinct species of microscopic plankton, single-celled marine organisms preserved in the Precambrian rock, dating back 2 billion years, intact. The word intact deserves emphasis. At that depth, the temperature is around 150 degrees Celsius. The pressure is immense, dozens of times greater than atmospheric pressure at the surface. The rock surrounding the fossils had been buried for 2 billion years, subjected to forces that pulverize and transform solid stone. By every standard model of how organic material behaves under geological conditions, anything biological at that depth should have been destroyed utterly, reduced to carbon smears at best, to nothing at all. The idea of finding recognizable fossils, individual organisms, their structures preserved in enough detail to identify them as 24 separate species at 6.5 kilometers underground, was not something anyone had thought to predict. It was not something anyone had looked for. The fossils were found because they were there, not because anyone expected them. The reason they survived appears to be the material that encased them. These organisms were not preserved in the limestone or silica shells that most marine microfossils occupy. They were encased in organic compounds, specifically compounds rich in carbon and nitrogen that formed a kind of molecular armor around the delicate biological structures. Carbon and nitrogen compounds, under the conditions present at that depth, are more resistant to the heat and pressure than the mineral shells that normally protect marine fossils. The chemistry of the encasing material appears to have been the difference between preservation and obliteration, a geological accident of chemistry that turned out to be, across 2 billion years of burial, exactly sufficient to keep the organisms recognizable. But the deeper strangeness is not the survival, it is the origin. These were marine organisms, single-celled plankton that lived in open water. The Kola Peninsula today is solid land above the Arctic Circle, hundreds of kilometers from any ocean. There is no ocean there now, and there has not been for an extraordinarily long time. 2 billion years ago, a span of time so vast it resists genuine comprehension, the arrangement of the Earth's continents was entirely different. The land masses that would become Europe and Russia did not exist in anything like their present form. The rock that is now 6 kilometers underground on the Kola Peninsula was once, impossibly long ago, at or near the surface of a world unrecognizable to us, covered by shallow seas inhabited by the earliest complex life that had yet appeared on the planet. Over 2 billion years, that rock was buried. Tectonic forces moved it, compressed it, layered kilometers of new material above it. The organisms in it died. The seas they lived in closed. The continents shifted. Ice ages came and went. The dinosaurs appeared and disappeared. Human beings evolved and built civilizations, and eventually, in the second half of the 20th century, built a drilling rig in the Arctic wilderness and began boring a hole toward those ancient organisms from the other direction. And the fossils waited for 2 billion years, in conditions that would kill anything alive today, sealed in their carbon and nitrogen armor, in the dark, under crushing pressure, at temperatures that would boil water. They simply endured. When the scientists examined them, they were intact enough to classify, 24 species, each one a message from a world so old that the sun itself was meaningfully different then, slightly cooler, slightly smaller. Each one a piece of evidence that life had been present on this planet far earlier and in far stranger circumstances than any of the surface rock record had suggested for that particular location. This was not a geological discovery in the conventional sense. It was not a correction to a seismic model or a revision of a crustal boundary. It was something closer to a communication across deep-time evidence that life's reach and persistence exceeded what anyone had thought to look for, preserved by a chemical accident at a depth where no one had thought to look. And it raised a question that nobody has fully answered since. If 2 billion-year-old organisms can survive 6 kilometers underground on the Kola Peninsula, what else might be down there, in the vast unsampled interior of the planet, that we simply have not yet found? Nobody had predicted fossils at 6 kilometers. Nobody had looked for them there. They were simply there. By 1989, the third branch of the borehole had reached 12,262 meters, 40,230 feet. That is deeper than the Mariana Trench is below sea level. It is taller than Mount Everest and Mount Fuji stacked on top of each other. A coin dropped into the borehole would fall for 50 seconds before hitting the bottom. And at that depth, the project ran into its final and impassable obstacle: the temperature. The scientists had modeled the expected temperature at 12 kilometers using every geophysical tool available to them. The models were not crude. They incorporated decades of seismic data, heat flow measurements, rock conductivity studies, and mathematical projections refined over years of preparation before the first drill bit ever touched the ground. The models predicted that at 12 kilometers depth, the rock temperature would be approximately 100 degrees Celsius. Hot, certainly. Hot enough to make drilling difficult, but within the tolerance of the equipment that had been designed and built specifically for this project. The actual temperature at 12 kilometers was 180 degrees Celsius, nearly double what the models had predicted. Not a margin of error, not an instrument anomaly, a fundamental miscalculation of how quickly heat increases with depth in this particular region of the Earth's crust, a miscalculation made possible, again, by the limitations of surface observation. The geothermal gradient in the Baltic Shield was simply steeper than the models had assumed, and there was no way to know that without going there. At 180 degrees Celsius, under the pressures present at 12 kilometers depth, the granite stopped being brittle. It became plastic. Not liquid, it did not melt, but it lost the rigidity that makes rock cuttable and drivable. It became, under those conditions, something closer to an extremely stiff, extremely slow-moving substance that would deform under stress rather than fracture. And this had a catastrophic practical consequence for the drilling operation. Every time the drill bit was pulled out of the hole for replacement, which, as established, happened constantly, the hole would begin to close. The plastic rock crept inward from all sides, squeezing the borehole shut, undoing days of work in hours. A hole that had taken immense effort and expense to open would partially seal itself before the drill could be reinserted. They were not just drilling through rock. They were fighting the Earth's tendency to heal itself, and at 12,262 meters, the Earth was winning. The rest of the world was hitting the same wall. Germany had launched its own super-deep borehole project in Bavaria, the Continental Deep Drilling Program, known as KTB drilling, between 1987 and 1995. The Germans brought their own ambitions and their own innovations. They developed vertical drilling systems specifically to keep the borehole as straight as possible, reducing the torque that had caused the Soviets so many problems with twisted drill strings. That technology is now standard throughout the oil and gas industry worldwide. The KTB borehole reached 9,101 meters before temperatures above 260 degrees Celsius stopped them completely. But they found the same surprises the Soviets had found. fluid-filled fractures at depths that should have been dry, hydraulic connectivity between rock layers kilometers apart, a deep crust that was permeable and chemically active rather than sealed and inert. A Dutch artist named Lotte Gaven lowered a microphone protected by a thermal shield down the German borehole. It picked up a deep, continuous rumbling from somewhere below, a sound that the scientists could not fully explain, something the rock or the fluid moving through it was producing in the dark. Gaven described the experience as hearing the planet breathe. Some people, when they heard the recordings, said it sounded like hell. The scientists were more measured. But the fact that something was audible at all, that the Earth at 9 kilometers depth was producing sound, continuous and unidentifiable, rising up through kilometers of granite, was its own kind of revelation. China entered the story in 2023, drilling into the Tarim Basin in Xinjiang, a project called Shendi Take-1, designed to reach 11,100 meters. The drilling required the world's first fully automated rig capable of reaching 12 kilometers, engineered with drilling fluids formulated to withstand temperatures above 220 degrees Celsius and pressures exceeding 130 megapascals. By March 2024, the borehole had passed 10 kilometers, becoming the second deepest vertical borehole in history and the deepest in Asia. And what it found at that depth overturned a different set of assumptions entirely. At over 10 kilometers underground, in conditions of extreme heat and pressure that conventional petroleum science had long predicted would destroy any hydrocarbon molecules, the Tarim Basin held natural gas. Commercial quantities. Flowing gas from Cambrian-era rock 500 million years old at depths where the standard models said oil and gas could not possibly survive. The hydrocarbons should have cracked into methane or been reduced to graphite. Instead, they were there, producible, economically significant, existing at depths that the entire history of petroleum geology had written off as sterile. Different countries, different geology, different decades, different goals, and the same fundamental lesson. The deeper you go, the more the Earth contradicts what you expected to find there. The Soviet project tried for 3 more years after 1989. Different approaches, different techniques, different branches drilled from new starting depths. The fourth hole, begun in January 1991, was stopped in 1992 at 11,882 meters when temperatures again exceeded the equipment's tolerance. A fifth attempt began in April 1994 and was abandoned in August of the same year, not because of temperature this time, but because the funding had run out entirely. In 1992, drilling stopped for what would prove to be the final time. If they had reached their original goal of 15 kilometers, scientists estimated the temperature at the bottom would have been around 300 degrees Celsius. Even today, in 2025, there is no operational drilling technology that could function in those conditions. The equipment simply does not exist yet. The project had reached only 1/3 of the way through the crust at that location. It had not come within 23 kilometers of the mantle. In terms of the Earth's radius, 6,371 kilometers, the Kola super-deep borehole penetrated 0.19% of the way to the center of the planet. And yet, what it found in that 0.19% overturned decades of scientific certainty. The Soviet Union collapsed in 1991. Funding evaporated. The scientific team was downsized and eventually dissolved. By 2008, the entire facility had been liquidated and abandoned. Today, the site sits in a state of slow ruin in the Arctic wilderness, rotting timber, scrap metal, the remains of what was once a small city dedicated to one of the most ambitious scientific projects in history. And at the center of the crumbling remains, there is a small, heavy maintenance cover embedded in a concrete floor. It is secured by a ring of thick, rusting bolts. Beneath it, sealed shut with welded metal, not because anyone expects anything to come out, but because a hole that deep is genuinely dangerous to leave open, is the entrance to the deepest artificial point on Earth. Tourists visit sometimes. They stand on the concrete floor, look at the rusted cap, and try to imagine 12 kilometers of dark, pressurized, geologically strange space spiraling downward beneath their feet. Locals, for a long time, claimed you could hear something if you put your ear to the cap. Sounds. Unusual ones. The story circulated in the early 1990s that drilling had been stopped because workers breached a vast, superheated underground chamber and heard screaming rising from the depths, the wails of damned souls. According to a tabloid report that spread globally and has never quite died. The story was published as fact in several countries. It was referenced in sermons. It made the rounds of early internet forums. In certain corners of the internet, it still circulates today as evidence of something supernatural beneath the surface of the Earth. None of that happened. The drill encountered no chambers. It encountered no screaming. What it encountered was something arguably stranger and more interesting. A planet that is fundamentally different from the one we thought we understood. The legacy of the Kola Super Deep borehole is not the depth record. Records are eventually broken. China is already the second deepest, and Japan is building towards something more ambitious still. The legacy is the lesson the borehole taught, forcibly and repeatedly, over 22 years of drilling, that the Earth's interior is genuinely unknown, genuinely surprising, and genuinely impossible to understand from the surface. Every major assumption the project set out to test was either complicated or overturned. The basalt was not there. The water was. The temperatures were nearly double the predictions. The fossils were real and intact, and 2 billion years old. The rock at the bottom was plastic. The gases coming up from the deep were unexpected in type and quantity. And every single one of these discoveries pointed toward the same conclusion. The models built from surface observation, however sophisticated and carefully constructed, could not substitute for the direct sampling that only a drill could provide. This has had practical consequences that extend well beyond the world of academic geology. Geothermal energy, modeling the science of identifying where heat from the Earth's interior can be usefully extracted, rested on assumptions about deep crustal temperature gradients that Kola's data forced geologists to revise. If temperatures increase nearly twice as fast with depth as the standard models predicted, then the locations and depths at which geothermal energy becomes viable are different from what was assumed. The map of exploitable geothermal resources had to be redrawn. Similarly, earthquake prediction models the attempt to understand where and why the Earth's crust fractures depend heavily on understanding how fluids move through deep rock and how that fluid movement affects the stress on fault systems. The discovery that the deep crust is not dry and sealed, but saturated with pressurized, mineralized water changed the baseline assumptions of seismic science. Water in rock under pressure changes how that rock responds to stress. It changes when and how faults slip. Understanding that deep water is present in places where it was not expected to be present is not a minor geological footnote. It is a potentially significant input into how we model seismic hazard. The engineering innovations that came out of Kola have their own legacy. The downhole turbine drilling system, the rotary bit, driven by pressurized mud rather than by a rotating shaft, became the conceptual ancestor of modern downhole motor technology used throughout the global oil and gas industry. The geophysical logging tools, developed specifically for the extreme pressures and temperatures of the Kola borehole, pushed the boundaries of what instruments could withstand, and the engineering solutions developed there became part of the foundation of modern downhole measurement technology, a project that never reached its scientific goal, left behind a toolkit that transformed an entire industry. And now Japan is building toward the next attempt. The The drill ship Chikyu, a vessel the size of a small city, equipped with 6 computer-controlled thrusters capable of holding position to within 50 centimeters against ocean currents, carrying a derrick taller than a 30-story building, was designed specifically for the project of drilling through the oceanic crust to retrieve the first ever sample of the Earth's mantle. The oceanic crust is thinner than the continental crust, roughly 6 kilometers in the target locations, compared to the 35 kilometers of continental crust at Kola. The plan is to drill in deep water where the mantle lies closest to the surface and to bring up, for the first time in human history, a piece of rock from below the Mohorovicic discontinuity. A piece of the mantle itself, unaltered, as it exists right now rather than as it existed millions of years ago when fragments of mantle reached the surface through volcanic processes. If successful, it would be the geological equivalent of the Apollo program. Not in scale or public profile, deep Earth science has never captured the imagination the way space exploration has, but in scientific significance. A mantle sample would answer questions about the composition and dynamics of the largest portion of the planet that have been debated since geology became a science. It would ground truth every model of the Earth's interior that has been built on indirect observation. It would be the difference, as one scientist put it, between having a live dinosaur and a fossilized bone. We are not there yet. The project requires political will, sustained international funding, and engineering solutions to problems that have not yet been fully solved. But the ambition exists. The ship exists. The knowledge of what is down there, imperfect, surprising, incomplete as it exists because of what was learned at Kola. The full Voyager comparison belongs here because it is the most clarifying way to understand the scale of what we do not know about our own planet. The Kola Superdeep borehole reached 12.2 kilometers into the Earth over roughly 22 years of drilling. In approximately the same span of years, the Voyager 1 spacecraft, launched in 1977, had traveled 16.5 billion kilometers and crossed the boundary of the solar system into interstellar space. We sent a machine to the edge of the solar system and received signals back from it before we managed to drill 1/5% of the way to the center of the planet we live on. We know more about what lies between stars than we know about what lies 12 kilometers beneath our own feet. That is not a rhetorical flourish. It is a precise description of the state of human knowledge about the interior of the Earth as of today. Beneath that rusted cap, 12 kilometers down, the granite is still slowly flowing. The ancient water is still trapped in its fractured channels. The 2-billion-year-old fossils are still there, unchanged, waiting in the dark. The Earth keeps all of its secrets down there,